So I think let's focus on that. Let's focus on how we get there, because I agree with you that they're going to look the same, right? So for a cation like this, right, the pattern of electron flow. This is an allylic cation, by the way. Right, the pattern of electron flow is going to be such that you want to do two things. You want to, well, really one thing. You want to share this plus charge over this whole system, right? And the way you do that is by finding your donor, which in this case is your pi bond, and then finding your acceptor, right? And then that's how you know how to or where to push your electrons, because you're going to move those electrons towards the acceptor. Are you following that?
Yes.
So in this case, we're going to do this, right? So we're going to take that. Now keep in mind that double bond is made up of a pi bond and a sigma bond. So we always want to work with the pi bond because it's more readily accessible. Those electrons are easier to disturb than the ones in the sigma bond. All right, so we take that pi bond and look at what I did. What is that? What is the start and stopping point of the arrow indicate? What it says is that the electrons are coming from the pi bond and they're ending up here between these two atoms. Do you see how the arrow stops between those two atoms?
Yes.
Mm-hmm. And so that means that the resonance form is going to look like this. It's not an oxygen, sorry. All right, that's H. And this is the plus charge is not going to be on this carbon. Yes or no?
Yes, I understand that.
Okay. If we did that for an allylic anion, let me show you the difference. The difference is that if I have the same generic structure, but instead I got a lone pair here. Now which one is the donor? Right. Remember, if you got a choice between a pi bond and a lone pair, you're going to pick the lone pair as your donor because it's more accessible. So that's my
Wait.
donor, and that makes the pi bond my acceptor.
Oh.
You following?
Okay. Yeah.
So now there's a different electron flow with a system like this. This is an allylic anion. Different electron flow. So now what I'm going to do, and what I will always do, no matter where I find this pattern, is I want to take this pi bond and put it here and turn it and take the lone pair and put it between these two carbons, and that's going to make a pi bond between them. And then if I do that, that middle carbon is going to have a problem in it.
Yes. So
Because it's going to have 5 bonds to it if I leave it. So then I take this pi bond right here. Let me erase this arrow. I'm going to take this pi bond right here and put those electrons onto that terminal carbon. You see that?
Yeah.
So now the resonance form is going to look like this, where I have a double bond here. And then here. Now my pair of electrons is now down here. And that carbon is negative.
Okay.
Right. So what I've done in effect is I've shared that negative charge over all 3 of those atoms. I've delocalized it over all 3 atoms. And I did the same thing with the cation up top.
Okay. So basically the difference is for cations, you are passing around the bonds, right? And then for the anions, you're passing around the lone pairs.
Okay. I feel you.
You
And
understand?
I think I do. I understand what you're trying to say. and the essence of your statement is correct.
Okay.
But let's say it in scientific terms. All right. So for the cation, what I did was I shifted the pi bond. Right.
Mm-hmm.
That's what I did. I shifted the pi bond over to where the plus charge is, didn't I?
Yes.
And then for the anion, what I did was I made a new pi bond with a lone pair, which caused the pre-existing pi bond to become a lone pair, but on a different atom. You following that?
Yes.
Mm-hmm. But you're right, though. The way you're thinking about it is right, which is good.
Okay. I just needed like a little saying to say in my head so I know the difference.
So here's the saying. All right. So for cations, you can say that the pi bond shifts. And then for anions, you can say this: lone pairs become pi bonds, and pi bonds become lone pairs.
Mm-hmm. Oh, okay.
You feel me?
Yeah. Yeah.
All right.
Okay. Thank
Question.
Go ahead.
Can you look at it at delocalization, like cradle balls, how they kind of bounce from one atom to the other?
Yeah. You're talking about like the when you take the two balls on the end and they're swinging and energy is being transferred between the three balls in the middle. Yeah, definitely.
Okay,
That's
that
a good
helps
way
me
to think about
picture it better for anyone.
That's a good way to think about that.
Thank you.
All right, so let's do some more examples of resonance. I kind of cut out a problem, and I want to do one that has a lot of meat to it. So I want to start with E right here, and I'm going to redraw this down below, and I'm trying to do this today so I can save these notes and send them to you, in addition to posting the video from the class. So I am recording, so let's just make sure. Yeah, it is recording. So let's take that example up top. Can everybody see my screen?
Yeah.
All right, I'm gonna take that example for E, right? That phenolic anion. So let's do that. So this is, let me make sure I draw the ring right. So I don't want to confuse anybody. I'm going to put my lone pairs in on oxygen. What's the first thing I need to identify in order to determine if I can do resonance?
Donor and acceptor.
Look at that. Who was that?
Miss Rollins.
Miss Rollins. Nice work. So I need a donor and acceptor, and they need to be adjacent. Is that right? And if you saw that, the handout that I sent or directed you to the other day, you really have like four scenarios that you're working with. And let me just put them over here, right? You have allylic anions. I'm just going to put a generic atom R here. You have allylic cations. You have allylic radicals, which we'll do an example of that later on. And then you also have, sometimes you have a case where you have two atoms bonded together and one is negative and one is positive, right? Those are the four patterns that you're looking for. Did any of y'all get a chance to watch that video I sent out with those patterns in it?
Yes, the ones with the shapes. I mean,
yeah, the little circles coming over the pattern. Okay.
Some of them were kind of difficult to follow for me. I think it's just because they were not in Lois structure.
Okay. All right, so let's look at that. So what pattern would this molecule fit out of all the four patterns over there? Keep in mind, those are the only four patterns that we're going to be looking for.
Dr. Russell?
Yes.
Can you scoot over to the four patterns a little more?
Can you see them now?
Yes.
Right. Those are the only 4 patterns I'm going to be looking for to find out if a structure or molecule or a functional group is able to do resonance. So which pattern would this fall into?
What's that third one?
The third one it's called a radical. It's only got 1 electron.
Oh no, that's not it.
Do you see the pattern here?
Sure.
Do you see it? Hold up.
I want to say the first one.
Yeah, it's an allylic anion in it. You got an atom with a negative charge that's right next door to a double bond. Is that right?
Mm-hmm.
So it falls into this pattern. All right. So knowing that, how are we going to move the electrons? That's the second part of doing this. Well, we did it up here, right?
Mm-hmm.
So what's the first arrow that you're going to put in?
So I want to say that
So that one of those long pairs on oxygen, I'm going to put it right there between this carbon, right, and oxygen to make what? A pi bond. Is that right?
Mm-hmm.
Yes or no?
Yes.
And then what's going to happen to the pi bond between these two carbons? Because you can see the pattern. These are the 3 atoms that I'm looking at. The 2 carbons and the oxygen. Don't worry about the other pi bonds yet, because we can't touch them anyway. Not yet.
It's well, I don't want to say it's gonna move, but technically that's what it's gonna do, and then you're gonna have your lone pair there.
So the lone pair is going to end up on the third carbon. Is that right?
Mm-hmm.
So what I'm looking for in order to identify whether I can do resonance is a 2-atom unit or a 3-atom unit with a donor and an acceptor adjacent to one another. And that's exactly what I have here. I have a 3-atom unit, right? Here, 1, 2, 3 atoms. The donor and the acceptor are next, and I have a donor and an acceptor. The oxygen is my donor, and then the pi bond is my acceptor. Is everybody clear on that? Anybody not clear? Say something. So what does the resonance form look like based on that first set of arrows? Don't just let me be drawing it too. Now you should be drawing it yourself, because we're moving at a slow enough pace where you can kind of be drawing it. Is that right? That's part of it, yes?
Yes.
All right. The other 2 double bonds over here we didn't touch, so we're going to put those back. Only thing I need to put in now is what?
Your lone pairs.
The lone pair on that 3rd carbon up top. Is that right?
Yes.
Man, that's like 10 electrons. Get it together, Russell. All right. I got to zoom in a little. And that carbon has a negative charge. Could somebody tell me why that has a negative charge?
Because it has a lone pair.
Mm-hmm. And what else? How do you calculate it?
It only has 2 bonds.
No, it's
Yes,
got
5
actually it's got 3
electrons.
bonds. Because what's not shown
1, 2, 3, 4.
is a hydrogen. There's a hydrogen on that on each one of these carbons, and there's 1 hydrogen on each one of these.
Okay.
So the hydrogen I didn't show, but it's there. So it's actually got 3 bonds and a lone pair. So I heard somebody counting to 5. Is that right? If you do valence minus actual, it will be 4 minus 5. So that carbon will have a -1 charge. That's why I did formal charge first, because you're going to see it a lot. All right. Do you see another pattern
You said, do we see a what?
Another pattern.
Mm,
Right. Let me put
yes.
this right quick. Do you see this is a carbon, that's a carbon, and that's a carbon. Is that right?
Mm-hmm.
And one of those carbons has a lone pair on it, and then the other two carbons are in a double bond, and they're adjacent to one another. Is that right?
Yes. So for
Okay.
this one, is it the electrons going to shift all the way back to
Eventually,
the last carbon? So
eventually, yes,
okay.
but you can't do it all at once, right? But you are right. Eventually, I'm going to get there, but I'm going to do this, right? I'm not going to change anything. It's the same flow of electrons that we did with the top example, right?
Mm-hmm.
Where you're going to take that pair of electrons and turn it into a pi bond, and take the pi bond and turn it into a pair of electrons, and they'll be on this last carbon right here. Anybody not see that? So what does that resonance form look like? I'm gonna give you a rule of thumb too about how to determine when to stop, because that's always a question. When do we know? How do we know when to stop? I'm gonna show you. So what would that look like? That new structure.
It would be a double bond at the top.
So a double bond right here, good. Is that right? One right here. The double bond is still to oxygen, yes. Where's that lone pair gonna be now?
It's
It's gonna be right there on that carbon.
Uh-oh.
Is that right?
Yes.
Yes.
All right. Do you see another pattern that you can work with?
The last, yeah, it's gonna be the
See that
last.
right there? Is that not the exact same pattern from the first two examples?
Yes.
It's the same. So when you get ready to do resonance, it's going to be the same electron flow, right? Because it falls into the allylic anion pattern. So that when you have a pattern, once you find the pattern, the way the electrons flow is the same no matter what. It always does the same thing no matter what. All right. Anybody got the last one drawn yet?
Okay.
Is that right?
Yes.
Just trying to make it look a little bit more presentable. Yeah. Anybody have that before I finish it?
Oh, getting there.
Getting it close. All right. So how many total resonance forms do we have?
4.
1, 2, 3, 4. We could do it. We could actually do another one. Do you see it? Somebody tell me what the next one would look like and where the pattern is.
Between that carbon with the lone pairs and then the pi bond.
It's right there, ain't it?
Mm-hmm.
So I could actually do this. Is that right?
Yes.
And let's see what that gives us. I promise you, if you can do resonance, the rest of this stuff in this class is not going. It's going to be a cakewalk to you. Right? It's going to give me that. So how many total structures is that? Is that 5 resonance structures?
Yes.
Right? So you had 1 donor and 3 acceptors. So you're going to get a minimum of 4 resonance forms. Right? That's how you can kind of gauge where to stop, or how you determine how many times you can do resonance if you sum up the donors and the acceptors. So if you look at that very first structure, right, you got 1 donor, which is the oxygen, and then all your pi bonds are acceptors. So you know you're going to get at least 4 resonance forms. And if you look down here, you got 1, 2, 3, 4. Does that make sense?
It does.
So if you add, I'm not going to say determine, I'm going to say estimate. Because for cations, it's a little bit different. All right, so if you add up your donors and acceptors, you can estimate how many resonance forms you'll get. All right, any questions about that one?
For the last one,
Mhm.
why is there only 1 electron? I mean, it's 2, 1, 2, 3, 4, 5 electrons on the oxygen.
No, my one of my long pairs just looks kind of jacked up. This 3,
Oh, okay.
they were just kind of smushed together. It's weird, like, because if I'm zoomed out, when I write on it, it just looks weird. But I can fix that. All right, is that better?
Yes, thank you.
All right. Any questions about that resonance form or that example?
Can you zoom out of it real quick?
Zoom out so you can see all of them.
Yes, please. Thank you.
Is that better? I can't zoom all the way out, but I can. Which ones are you trying to write down? The last ones or the first ones?
The last one.
Okay. I think I can fit all 4 of those on the screen. What about that? Can you see all 4 of those?
Yeah.
Okay, cool. All right. Any questions about resonance? So what's the strategy? First, find your pattern, then find the donor and acceptor, and then put the electrons in. I put the arrows in to show how you're moving electrons.
So how do you know when you like found all of the resonance structures?
So if you notice here in the last resonance form, I have nowhere else to go except backwards, right?
Yes.
I can't do another resonance form from that. Anything I do from here will be basically going back to the resonance form that preceded it.
Okay.
You following that?
Yes. So like once you get about the same structure on the last one as the first one?
Well, it's not. It won't always be like that. But for this is a kind of a special circumstance. But my suggestion is again to add up the donors and the acceptors to get an estimate of how many resonance forms you should get.
Okay.
And that way you'll know at least that you got based on their original structure, you'll know that you should get at least 4 or 3 or 2 resonance forms of that. You follow me?
Okay. Yeah.
All right. Let's do another example. All right. So that was E. E is pretty. That's one of your more difficult resonance forms. Let's try C. What pattern does C fall into? Can y'all see that? What pattern would that fall into? If this is my first
Pattern 2.
pattern 2. Who was that?
Amari.
All right. It's a cation, isn't it? It's an allylic cation, so it will fall into that second pattern. You follow me?
Yep.
Now, what did we say? How did we say the electrons are going to flow for that? Right. We showed it right here. What you end up doing is shifting the pi bond over to where that plus charge is. Again, the whole idea behind doing this is to stabilize either a pair of electrons that doesn't want to just sit on one atom, or a charge that's on an atom that I want to make neutral, right? It's kind of like putting a fire out. If there's a fire burning on this carbon and I got a way to eliminate it, then I do it, right? And what that does is end up shifting the fire to a different carbon. But if you keep going back and forth, which is what this arrow indicates, then you're basically keeping the fire to a minimum. I'm gonna put it like that. All right, so let's look at C. I'm gonna draw it out down below so we can walk through all the resonance forms. Any questions so far? I know this is it's sucky, but I promise you, it's gonna be to the good once you learn it and once you grasp it and get what's happening. That's that, and that. Is that right? So this is a cation. What am I gonna do here? So I know where my donor is in this case. Where's my donor? Help me out, somebody.
Pi bond.
It's the pi bond, right? And then that makes the cation my acceptor. So for this particular example, I'm going to do this. I'm going to shift that pi bond over to there, in between these two atoms right here, this carbon and this carbon. And let me ask this question before I go any further. Is everybody okay with the fact that this ring, at every vertex of this ring, there's a carbon? But I just have it written in skeletal form. Is everybody okay with that?
Yes.
Yes.
All right. Okay, so that first resonance form, I'm gonna push that pair of electrons out of the ring, and then I'm gonna have this. Everybody agree with that? Not touching the other two pi bonds yet. Where's my plus charge gonna go?
Where the
It's gonna go to this vertex, right? Yep, is that right?
yes, because it only has 3 bonds.
Yes, there's a hydrogen that's not shown, so that's exactly right. Let me ask you a question. Why did that carbon, and this is a dumb question, but I'm asking anyway. Why did the carbon become positive? How do you make atoms become positive?
Take away their electrons.
Take away the electrons. What does that arrow going from that pi bond mean that I'm doing? It means that I'm taking electrons away from that atom, this atom right here. Is that right? And when I do that, that atom is going to become positive because I broke a bond from it. I broke a pi bond from it. Anytime I take electrons away from an atom, that atom becomes positively charged. Is that okay?
Yep.
All right, let's do another. Let's start here. Again, it's skullduggery, but we got to do it because I promise you, if you master the skill of resonance, you can do anything in this class. Everything else becomes cake because you have so many different concepts that are tied up in this one concept. Formal charge, polar covalence. All of this stuff is tied up in resonance. So where's my pattern here? I got three atoms right here: carbon, carbon, and carbon. Everybody agreed that those were all carbons on those vertices. What's my pattern?
You
Can
move.
see it? You see it right there?
Yep.
So so now I've identified the pattern. I need to find what's my donor, what's my acceptor, which would be what? Which one would be the acceptor?
The carbon with the positive charge.
The carbocation, good. And that makes the pi bond the donor. Is that right?
Yep.
All right. Is that Amari? Can you click on the it's a view options, I think, and click on annotate and put the arrow in there. Show us where that where the pi bond is going to shift to. It's like a thing that says view options, I think.
Okay, I see it.
And click annotate, and you can use your mouse pad to draw the arrow in.
My arrows will be bad.
I would use the little squiggly line.
Okay.
Yeah, that'd be easy because those arrows are kind of weird.
This.
Okay. Great. Perfect. Can anybody see that? So the arrow is going from, let me kind of use a different color to cut. So we're going from here to here. Or you could have written it this way. It doesn't matter. Either way is fine. Right? So then the new structure, what's that going to look like? It's going to look like the ring is not changing. So I'm not changing the shape of that. The CH2 is still out there. I'm putting this pair of electrons here as a pi bond. This pi bond didn't move, and now my plus charge is here on the vertex. All right, appreciate that, Maury.
No problem.
Is everybody okay? If you're not okay, say something. All right, can I do it again? I see I got the same pattern right here, don't I?
Yep.
So boom, I'm going right here, shifting that pi bond over, and I'm going to have another resonance form that looks like this. Boy, that ring's horrific. Yes?
Yep.
And then I have the same pattern right there, and I can do another resonance form. It's very similar to the first example, except for it's a cation and not an anion. So I'm going to shift this over to here. And I'm going to call your attention to something too. All right, can y'all see that? How many resonance forms is that? Is that 4 total?
Yes.
Yeah.
Mm-hmm. So does that formula hold up where we have 1 donor and 3 acceptors, or 1 acceptor in this case and 3 donors? So we're going to get it at a minimum, we'll get 4 resonance forms. Yes or no? Amari, can you hit the clear button so that arrow can
Oh,
get?
yeah.
I appreciate it.
I just missed all of that. My connection went out.
Oh Lord have mercy. Well, I am recording this though.
Okay.
Yeah, and I'm going to send this notes out as a PDF. I'm going to put them in a folder on Blackboard. All right. Any questions about that example? Let's go back up here. Which one do y'all want to do next? out of the highlighted ones. We've already done C, and we've already done E. What do you want to do next?
Can we do B?
Yeah, we can do B. No problemo. Before we do it, do you see the first pattern that we're gonna deal with? Let me put. There's a long.
You would do the minus charge first.
Mm-hmm.
Do the double bonds.
So do you see it right here? In that 3 atoms with a donor and an acceptor right next to each other? Is that right?
Yes.
Yeah.
Mm-hmm. So my first, and what pattern does it fit? Cation, anion, radical.
Anion.
Anion.
It's an anion. So we already know how those are. It should be clicking now. What pattern of electron flow we're going to use, right? What's going to happen to that lone pair?
And make a pi bond.
It's going to be used to make a pi bond right here, isn't it? I got to take that pen size down a little bit. Is that right? Now, what's going to happen to the pi bond between the two CHs?
Don't you have to
Wait.
break it?
I got to break it. And I got to put it right here on that carbon, don't I? Yes or no? All right.
Yes.
Don't be scared to say, yeah, man. Be confident. If it's wrong, at least it's not wrong on the test. It's wrong in here, so we can correct it. Don't be scared. So I'm gonna draw this as CH. That's negative. Everybody agree with that? And then this would be CH with a double bond to CH2 on the end. Is that right?
Yep.
Can I do it again? Do you see another pattern? Do you see this pattern right here?
Yeah.
3 atoms with a donor and acceptor adjacent to one another. Is that right? This
Yep.
is okay. This is for lunch. What is the name of this functional group?
Carbonyl.
Carbonyl.
Mm, mm, mm. That was too easy.
That was 2.
Who went first?
At me.
Me. No, it was me.
Can't be both of y'all now. Somebody
It was definitely me.
definitely who?
Me.
Amaria.
Lindsay.
Look at Lindsay trying to cheat, but you cheat. It was me. You didn't even have your mic on. It was me.
I sure did.
Yeah, I know you didn't. Amaria?
Yes, sir.
Is it Rollins?
Yes, sir.
All right, I got you. I think I'm gonna split lunch today because I don't want to leave Amari out because he's been kind of toting a lot of weight too.
Yeah.
So I'm gonna buy both of y'all lunch today.
Thank you.
Appreciate
it.
Yeah, just put your cash app in the chat box.
Okay.
All right. Let's go back to here. What's my So I've identified my unit. Is it an anion? Is it a cation? Is it a radical? Or is it a 2 atom? It's not 2 atoms, right? We already know that. That's out. So what's next?
The anion.
It's an anion. So how am I going to move the electrons? That's the next step, right? Identify the pattern, figure out which one of the 4 patterns it is, and then find my donor, find my acceptor, and then push the electrons. What do? Where are the electrons going in this case?
Or not to carbon, but to the form of pi bond.
Right here.
That carbon.
Is that right? Can y'all still see that?
Yes.
Yeah.
Okay, I just want to make sure I didn't zoom in too far. So that's that plus what? And then I also have to break this bond, this pi bond. Let me put some electrons on oxygen too while I'm at it. So that resonance form is going to look like this. Not like that. Is that right?
Yep.
Mm-hmm. All right. Is there anything else I can do with that? I'm done, right?
Yeah.
The only place I can go now is backwards. So that for B, those are the two resonance forms that you could draw. Right? You always want to look and see if you got another pattern that you can deal with. Even if, once you start, you always look for that to see if you can do it again. All right. Any questions so far? There's another part of this handout that we're going to go back to and work on some of those examples too. Right? We've done everything. We might as well just do H because H is the last one. Right? And let me put, I'm going to draw H down below because I'm not going to have enough room to deal with that. I think H looks something like this. Just didn't have a lone pair. Is that right? Got it.
Yeah.
All right. So now let's apply our strategy. Let's look for a pattern. Once we find the pattern, identify donor and acceptor. Once you do that, you put the electrons in. Right? That's the pattern you should be following for any resonance problem. Find the pattern, identify the donor and acceptor, and then push the electron. So where's my pattern? Do you see it here?
Yeah.
You got 3 atoms right there. Is that right?
Yep.
Which one is the donor? And how do I know what a donor is?
The donor's the carbon to the form.
Right?
Okay.
My donor is always going to be a what? Is it either going to be a lone pair
Or
or a
can
pi
I?
bond?
Or pi bond.
Right? And then my acceptor will be a pi bond or a cation or an electronegative atom. Right? Because we've seen that too. And I did not misspell atom with 2 T's. I know, yeah, that'd be all over Snapchat. Child, he's so dumb.
No.
You can't even spell atom.
Okay.
All right. So now we've identified this as a allylic cation. I'm sorry, anion. Right. Where the electrons are going to go. This does not change. Once you find that pattern, it's the same exact flow of electrons. It never changes. The lone pair is going to become a pi bond, and the pi bond is going to become a lone pair on the vertex adjacent to. Right? This is not negotiable. It's the same exact electrons, same exact arrows, everything. Is that okay? So what would the resonance form look like?
There'd be a double bond, right? Carbon that had the 2 lone pairs changing to a double bond, and then there'd be the negative charge and the lone pairs would be
Is that right? Is that what you mean?
carbon 2. Mm-hmm.
and then boom, like here,
Which
right?
way are you supposed to count carbons? Like,
Say
so
that
where the
again.
first vertex is, would that be carbon 1 that's next to the double bond?
You mean, yeah, you can do that. You want to number them, you mean?
Mm-hmm.
Yeah, it's up to you. I would, for clarity, I would always start with where my donor is. So I'll call that 1, that'll be 2, and that'll be 3. Even though that 1 looks like it's high. My bad. Right? That's fine if you want a number. You can not numbering is arbitrary. It's just figuring out or being able to recognize that it's a pattern, right? It's a 3-atom unit. And it falls into the anion category. Can we do another resonance form?
I think you could do like one more.
We can do it right there, can't we?
Mm-hmm.
Yep.
All right. Anybody want to put the arrows in? Don't be scared now. Come on. Might as well
Sure,
do
I
it.
will.
Go ahead. Who was that?
Kayla.
Come on with it. Okay, good. Great. Man, that's awesome. Nice work. So then that's going to give me a structure that looks like this. Is that right? Boom here, O minus, and then boom. Yes or no?
Yes.
Yes.
Let me put some lone pairs in here. Yeah. Good. Good job, Kaylin. Nice work. All right. We can't do anything else with that, right? Except go backwards.
Right.
Mm-hmm. All right. Let me give you an example of a radical. Let's do that because you're gonna see that again. Let me just take. Let me do this so we can do it more than once. So this is an example of what we call a radical, right? All a radical atom is a single. It's an atom with a single unpaired electron. I don't know why this has a lag? Right, so it's got a single. Can you see that over that CH2? That's just a one electron. It's just a dot, right? So the radicals. Oh, Kayla, can you hit the clear button to clear your arrows off? So the radical, it can also do resonance, and it's the same thing. I see this pattern right here. We'll call that CH2 the donor since it has an unpaired electron, and we'll call the pi bond the acceptor. The difference with the radicals is the type of arrows, right? Remember, if I use a double-sided arrow like that, that means I'm moving 2 electrons. If I use a single-sided arrow, that means I'm using 1 electron, right? And so with radicals, you always use these single-headed or arrows, or we call them fish hooks. You always use that. So I'm going to show you in this example how these electrons would flow. So you have 1 electron here. You're still doing the same thing though. You're still trying to delocalize that electron. I'm going to take 1 electron from this pi bond and put it here. And I'm going to take the other electron and put it right there on that carbon, on that vertex. Are y'all following that? What that means is that I'm going to end up with a double bond here, and my radical is going to be on the other carbon in the unit, the 3rd carbon in the unit. Yes or no? Can you see that? So let's see what that would look like. I'm going to erase this down here. All right, so it would look like this. Where not a radical, it's crappy. Not a radical is on this carbon right here. Is that right?
Yeah.
Mm-hmm. Do you see another pattern that we could do that with? You see this pattern right here now? Same thing, isn't it? That electron is not, I'm not happy with that. Hold on. That's better. All right, do you see that second pattern that we can do resonance with?
Yes. I have a quick question.
Go ahead.
So is the electron always going to be shown like in the skeletal form for the radicals?
Say that one more time. Well,
Like will the electron be shown, or is it just something we
oh,
kind of
you
have
got to
to?
show it. You got to show the electron. If you don't show the electron, like let's say up here, right? I got this as a CH2. Without that electron there, what is that? We could say it's a cation or anion, right? Because it's only got 3 bonds to it. So I have to put the radical in there.
Okay.
Yeah, I have to show that. I don't have to show the H's, but I got to show that if I have electrons, those have to be shown. That's a good question. All right. And every time you have an allylic radical like this, it's gonna be those same 3 arrows. You're gonna split the pi bond in half, and then you're gonna use the 1 electron from the pi bond and 1 from the radical to make a new pi bond. It's the exact same 3 arrows. I don't care even when you do it next semester in part 2, it's gonna be the same. Never changes. All right, what would you do here? Keep in mind we're going this way now.
Use one of the arrows to move just the 1 electron, and then like you said, use
Like
the
that?
yeah, and
With
then the
Fisher,
pi
right?
bond, move it half of it to the
Here?
other way.
Mm-hmm.
Yeah, and then the other half to the one on the left.
Like that?
Yeah.
Good. So then this is a CH2 with 1 electron on it. All right. Now,
Okay, makes sense.
yeah, let me say this too real quick before we stop, because we're going to have to stop in a minute. I want you to understand something. When we're talking about these electrons moving and all this stuff, they don't just float around in space, right? Every one of these carbons has a p orbital on it. Right? So that electron is in a p orbital and it's able to be shared with the other p orbitals that are already existent. And that's why they have to be adjacent, right? If this p orbital right here was 1 carbon away, you couldn't share those electrons. But the fact that they're adjacent, they can all talk to each other, right? So it will be the same thing down here, right? If those orbitals are not close enough to overlap, then you can't share electrons. That's for any resonance, whether it's an anion, a cation, it doesn't matter. All of these structures are going to have p orbital overlap. Let me go back up top, right? So something like this one that we did first, you got p orbitals here, and then you got p orbitals here, and then here, and they have to be able to overlap. Right, so that's really the heart of being able to share electrons, is being able to have orbitals that can overlap. All right, so are there any questions? I'm gonna save these notes too as a PDF document.